So we have seen that how to resolve hash collisions using chaining. Okay, so where multiple keys which are hashed to the same slot are connected with each other using a linked list. Now there is another form of collision resolution which is called open addressing. Okay, so the concept of open addressing is that we will not use any kind of chaining, because chaining needs to store the pointers to the next element in the linked list, and that eats up some of the memory space. Then why not use the whole memory space in the form of just the table and kind of bring in that the chain concept in the in virtual mode inside the table itself. That means like in the same slot, suppose 5 keys are being chained. So within that, instead of chaining, if you use the open addressing, we go to the first slot, and then we see, okay, in the same slot another element is being hashed. So what we do, so let's see this. So suppose in this table, so there is a slot here. So this one element is being hashed here. So now another element which also comes here in chaining, what we'll do, we'll create a linked list and store it here. Okay, so now we have to set pointers that will eat up some memory. Instead, what we are doing, we said, okay, we have some strategy. Just assume we say, okay, so this one is the next one. If this is having collision, we'll go to this slot, okay, where we'll store that next element which is coming to the same slot. Similarly, if a third element comes there, from here we'll find that, okay, this is going there. We will not have any such pointers. Actually, this is actually, we just calculate what is the next slot to which we can put that element, so that when we are trying to search for that element, we will also find in that manner. Okay, do you understand? So we will not have any chaining. Instead, the next element which slot which hashes to the same slot will calculate another location and store it there. Then from there, if there's a second collision, we first search here, then we search here, then we go to a third location. So these are kind of fixed, that we know that this location are the one we will search. So there is a big problem here. What if this element is being deleted? Okay, so if this element is being deleted, technically, as I said, we first search here, then we search here, then we go to the third location. But if the second element is somehow deleted, when we are trying to search for one of the elements, suppose this element, we will have difficulty in finding, because we will come here, this slot should be filled, and then we see, oh, this is empty. Then how come? I'll probably not even look for in the third slot. But this is more like that chain kind of thing. So if one of the in the middle element is broken, then that we will not be able to find that location, this location based on this location, because there is no element now. So deletion in open addressing is a little bit difficult. We have to somehow mark that this element, we will not just remove it, we'll say it's like deleted, so that it's considered in the algorithm when we are trying to search this path. Okay, so now let's see, based on this concept, that's the basic idea. So instead of having to store the pointers, why not use those memory locations to kind of extend that table? So now, because this is just the table itself, there is a chance that the table will fill up. Okay, in that case, we'll just say that, okay, hash table overflow. So now let's see, resolving hash collisions by open addressing. So this is the concept. Okay, so no storage for links and pointers. As I said, we do not want to store links and pointers. So you want to use that same memory location for the table itself. So the probe table systematically until an empty slot is found. Now there are multiple probing strategies. We'll talk about it. Before that, as I said, this is one strategy. Okay, if it's not here, then let's see here. Then it's here. So this is a probing strategy. There are multiple probing strategies which we will study. And we are trying to say we'll keep probing the table systematically until an empty slot is found. Okay, so this is a kind of a formulation for that. So hash value is the universe of keys, multiplied. It's like a exploring the entire space. How many probes are coming, and they has to match with one of the slots. If it does not match, that means all the slots are full and it's a table overflow. To summarize it, we say that for every key k, or every incoming key, the probe sequence hk0, you do the 0th position, then the first position, then the second position until the all m-1 position. It should be a permutation of 0, 1 until m-1. That is all the position. You keep looking using some strategies until you find an empty slot or there is no empty slot, which is a hash table overflow. So if you do that, then every hash table position is eventually considered as a slot for a new key as the table fills up. Okay, as I said, every slot position is can be a position for a new key until the table completely fills up. We could store the linked list for chaining inside the hash table. Okay, we could have stored that, like using that pointer, we could have stored that linked list of open address of chaining in the open addressing, but we don't want to do that. We don't want to waste those memory spaces. Okay, but open addressing avoids pointers completely. Instead of following pointers, compute the sequence of slots to be examined. We just compute what should be the next sequence and we go there and we store it. So that's why if you delete some of the middle element, computing, because computing this slot will be depending on this slot, computing this slot will be depending on this slot. If this slot is deleted, the element, it will be not possible to compute this element, okay, the slot for that element. So deleting key and open addressing makes it difficult. Okay, in that case, if you have a lot of deletion involved, so it's better to use chaining instead of open addressing. So as I said earlier, the table may fill up if n is not less than equal to m. So that means number of incoming keys are more than the number of slots in the table may fill up, in which case you cannot use any more slots in the open addressing. So after introducing the open addressing concept, let's go to the linear probing, which is one form of probing using which open addressing method is being implemented. Okay, so we try to find where in the table the next slot we search. Open addressing avoids pointers, so instead following pointers, you compute the sequence of slots to be examined. So what is the next sequence of the slot to store a key which is colliding with the already existing key. So we keep finding this slots. Now a linear way of finding this slot is called linear probing. So how it works? So the method of linear probing uses a hash function h of ki equal to h prime k plus I modulo m. Okay, so here h prime k is another hash function which is called the auxiliary hash function, using which we find the first slot for a particular key. Okay, so this is a auxiliary hash function where using which we find that from the universal set of keys where exactly it should first map into. Now if that is full, we probe the table and try to find where is the next slot where that key should go. Now you see here, so this value of I, we keep adding the value of I starting from 0 until m-1. 0 to m-1 is because if it's we take a division hash function by division, then it can wrap around. Suppose a key should go to position 7. Now if position 7 is full, we keep checking linear fashion by incrementing I by 1, 8, 9, 10, 11, 12, and then we wrap around and start from 0 until suppose this is slot K, slot P is until P-1, that means until one slot we keep checking. So linear probing will do maximum number of m probings for a particular key. Okay, if you consider the first one as is not the probing, as actually finding the correct should be the true location, then we say m-1 number of probings are there. Now let's see, this is the best understood using an example. Okay, so let's see an example with a sequence of keys which is to be inserted into a hash table given here with 13 slots. So m equal to 13, and the auxiliary hash function h prime k is actually k modulo m. Okay, so that's the division method. So k modulo 13. Now I have calculated here for all the keys which slots they actually should go, the first time which slots they should go. Now let's consider 18 modulo 13, which is 5. So I have to put 18 in slot 5. Okay, so I write 18 here, 18 is done. Next what comes in is 41. 41 modulo 13 is we get the first position, which is 2. So we write 41 here, okay? So this is done. Then comes 22. 22 modulo 13 is 9. So it will go to the position 9. Okay, so this is done. Then comes 44. Okay, now 44 modulo 13 is 5. When we go there, we find that's a hash collision. Okay, so what we do, we try to find out using now this position, okay, h prime k plus I. The h prime k gives you 5. Now start from I equal to 0. So this position 5 plus 0 is nothing. So when you go for I 1, so we go for the next position, okay? So that's this position, and we find, okay, this is the position which is empty. So we put 41 there. Now you see there is, sorry, 44. Now you see here, so suppose another key comes at this moment, which should go to, this position 5. Suppose this 31 comes in. So in that case, 31, we will try to see whether 31 goes in here or not. It's full, so we search next position. It's full, so then you go to the next position and write 31 there. So you see all the keys which should actually hash to the same location, they linearly they form a cluster. Okay, this is called the primary clustering problem. Okay, this is the primary clustering problem is there in this kind of hash table, and this actually delays the search method. Okay, if we want to search 31, I have to go here, search again. In that way, if all the keys actually map to the same slot, the worst case search time will be the length of the entire table. So this is a problem here. But after 44, what comes in is 59. 59 remainder 13 should go to 7. 7 is empty, so 59 goes in here. Okay, so now you see within that cluster another element joins, which is actually not supposed to be hashed to 5. This is in its correct position, but in this growing cluster, this is actually this procedure is called unrelated key clustering. So this is an unrelated key, but it's also clustering. Now let's see the next element, which is 32 modulo 13 is 6. So 32 should go to 6. Okay, so that's also an unrelated element, but 6 is full. So we try to check 7 because a linear probing. 7 is also full. Then we go to 8. So 32 goes to 8. Okay, so now then 32, 59 and 32 are done. Then comes 31. 31 modulo 13 is 5. So we cannot have in 5, we cannot have in 6, we cannot have in 7, we cannot have in 8, we cannot have in 9. So 31 goes in position 10. You see, if we try to find 31, I have to keep looking, the length, so the searching time will increase. So now the last one is 73. 73 modulo 13 is 8, so it should go to 8. But when you go to 8, we find it's full. The slot is occupied. Then you go to the linear one, 9, 10, and 11 is available. So 73 goes to 11. So I hope you understood the concept of linear probing. So it will, if there is no place, it will wrap around and start searching from the beginning until it finds an empty slot. And whenever it finds one, it will insert it there. So when you actually search it, you will follow the same sequence. So if suddenly some element in the middle is deleted, it will be difficult to find. So in our coding assignment, we will see how to implement the deletion in the open addressing kind of table, and you have to learn that while doing the coding assignment. After the linear probing of finding the position in the open addressing type of hash table, let's talk about the quadratic probing. Okay, quadratic probing is another another method of probing. Method of quadratic probing that uses hash function where hki equal to h prime k plus c1 times I plus c2 times I square. Okay, c1 times I and c2 times I square mod m for I equal to 0 to m minus 1. So here c1 and c2 are some positive auxiliary constants. Okay, so you can set the c1 and c2 and m properly to make this open addressing type probing for open addressing very efficient. So c2 cannot be equal to 0. So in general, it's like h prime hki equal to h prime k plus I square, if assuming C2 equal to 1. Okay, so this is the one you will find most of the examples and all stuff. So now here, if we use the same example, you know, that like before, these are the input keys, m equal to 13, h prime equal to k, remainder 13. You can see here, as I said, I can vary from 0 to m minus 1. So I is initially, you know, for I equal to 0, just forget it. For 1, it's 1. I go to 2, then this thing becomes, you know, go to the second position, sorry, 1, and then you go to 4, then we go to 9, then we go to 16, in that way. So it's not linear like before, you know, right next to 1, right next to 1, which was resulting in primary clustering. But this is like 1, the first position, then the 4th position, then the 9th position, then the 16th position. In that way it will, until the, you know, closest to the M, and wrap around. And then but there is a problem. If two keys have the same initial position, suppose both of them are hashing into a position 5, then what is happening? Then actually this you know, this sequence of probing will become same for both of them. So like see this, for this example, 18 modulo 13 goes to 5. Okay, so we write 18 in place of 5. Then 41 goes to 2, there is no collision in these places. 22 goes to 9, so there is no collision here also. Then we have 44, which goes to 5. Okay, so if 44 goes to 5, we will put in this formula, assuming C1 equal to 0 and C2 equal to 1, and then this formulation, then 5 is full. Then we go to the next position, which is considering I equal to 1. So that is 44 goes to the position 6. Okay, so now if the 59 goes to the position 7, so this is okay. Then 32 goes to the position 6. If 32 goes to the position 6 and 6 is full, initially we do go to the plus 1 position. Okay, so these are all plus. So this is position 6 plus 1. So that is 7, 7 is full. Then we go to the position 6 plus 4, that is 9, that is also full. So what we do, 6 plus 6, initially 6 plus 1, 7 is full, 6 plus 4, that is 10, which will go to 30, it's 32, will go to this position 10. Okay, now we have 31 modulo 13, which should go to 5, but 5 is full. 5 plus 1, 6 is also full. Then 5 plus 4, 9 is also full. Then 5 plus 9, 14. 14 means you wrap around. Okay, so it's here. 14 means, that means it should go here. So that is 31 should go to here. Okay, and then 73 should go to 8. 73 should go to 8. 8 is empty, so you can write 73 here. So you see that if for the same, if it's the same primary position, then the probing sequence will also be the same, because this probing sequence is then whatever with the same primary position, plus 1, plus 4, plus 9, plus 16, in that way, the quadratic probing. So that is called secondary clustering problem. I hope you understood the concept of quadratic probing. Now there is one more concept which is called double hashing. We will see that. Okay, so the third form of probing is called double hashing. So from the name you can find out that double hashing is that 2 times we generate hash values, unlike the previous two, like linear probing and quadratic probing. So the double hashing has the highest chance of being close to the simple uniform hashing, where the randomness is most prominent. Okay. It's not real randomness, it's pseudo random. Anyway, so method of I should say double hashing here. So method of double hashing uses double hashing uses hash functions h of ki equal to h1k plus I times h2k. Okay. So mod m, where I varies from 0 to m minus 1. And you see here, this is the first time is the h1k and the second one is the h2k. The first one, h1k, is like the auxiliary function we designed before, and we will use the similar. And h2k here is also an auxiliary hash function. Okay, so now if we see this, h2k should be primed to the size of the table M in such a way that the whole table can be searched in a much more efficient manner, unlike the more predictable linear and quadratic type of searching. Okay, so it's for example, suppose the first position is 5, then 5 is full, so there's a collision. So the second position we try to find, that can be anything like 257 or 7981. So in that manner, it should be generating the h2k in such a way that it kind of searches the whole table. So it's for every value of h1k, there can be multiple values of h2k generated. So it's like m times m searching. Okay, so it's like a m squared number of positions they will generate, and that makes the double hashing pretty efficient. Now let's see the same example where h prime in the initial, h1, it was k modulo 13 for this table, and where m is 13, and assume, so the for the h2k we assume that it generates odd numbers if m is an even number. So here m is not even, m is 13. So here this is from the book, this is one way of generating it. So we say 1 plus k mod m prime, where m prime is another number which is like a little bit smaller than the size of m. So it can be m minus 1, we have taken it's like m minus 2, like that was 13, so we make it m prime as 11. So now you see it will be given in the exam, what will be the value of that hash function. Now you see the h1k we already calculated earlier. Based on that, we have to calculate h2k. We have only shown for 1, and based on the collisions, we'll calculate more. Okay, so let's see first. 18 goes to the position 5 like before. 41 goes to the position 2 like before. 22 goes to the position 9 like before, and then 44 again should go to the position 5. Okay, so based on that, now I have to calculate h2k, which is 1 here, because 1 plus k mod m prime. K mod m prime is 44 mod 11, which is 0, and so there's 1 plus 0 is 1. So 44, now it will be h1k, that is 5 plus I equal to 1, so 1 times 0 times 1, then 1 times 1, so 5 plus 1 6. So this should go to the position 6, 44. Okay, so now let's see, 59 should go to the position 7, so 59 goes to position 7. Now 32 should go to position 6, so position 6 is full, so we have to calculate for 32. So for this one we have to calculate the h2k. So h2k is 1 plus 32 mod 11. Okay, so that is 1 plus 32 mod 11 is that is 10 here, so that is 11. Okay, so initial value was 6 plus 11 plus 6, or 6 plus 11, 17 mod m, that is mod 13. So 6 plus 11, 17 mod 13 is 4. Okay, so position 4, 32 will go. I hope you are understanding. Now let's see where 31 will go. 31 should go to 5, but 5 is already full. So for 31, we have to calculate h2k, which is 1 plus 31 mod 11. Okay, so that is 1 plus 9, that is 10. So now it is 10 plus 5 mod 13. So that is 2. Position 2 is still full. Okay, 41 is there. So now we have to calculate for 5 plus 2 times 10. Okay, so that is, and mod 13, so that is equal to 10 to the 20, 25 mod 13, so 12. Is it 12? Yes, 12. So 31 will go here. Okay, so that is, you see, I times this is this I times h2k. Now initially I was 1, now I is 2. If that one was not okay, then I will be 3, in that manner. Okay, so now let's go for so this is done. Now 73 should go to position 8. Position 8 is empty, so we put 73 here, and this is done. So as I said, it searches for m square different probing sequences are generated. So double hashing is the most efficient method for open addressing probing concepts, and it is useful when we are doing open addressing. Thank you.